Air travel is an essential part of our everyday lives, but it comes at a tremendous cost to our world. With carbon emissions contributing to global warming and climate change, there's a growing worry about its environmental impact. But what if we could develop carbon-free air travel? What is the impact of electric plasma jet engines on sustainable flying and on the aviation industry in general? Scientists have provided a revolutionary and shocking game changer by unveiling their latest invention, an electric plasma motor that will already revolutionize the world of air travel. This revolutionary new engine reduces carbon emissions from plane travel, creating a more sustainable future. This video will look at the remarkable plasma electric engine, how it works, and how it can be used in aviation. Join us as we delve into this extraordinary technology and find out how it has the potential to forever alter the face of aviation travel. The development of plasma engines has received increased interest in the realm of space exploration in recent years. Plasma engines, often known as plasma thrusters, are electric propulsion devices that utilize plasma to generate thrust. The technology is still in its early stages, but experts believe it could hold the key to carbon-free air travel. Unlike other propulsion systems that rely on chemical processes, plasma technology is already used in aerospace. Plasma engines employ electric and magnetic fields to ionize a gas, commonly xenon, argon, or krypton, resulting in plasma. The plasma is subsequently accelerated, creating a force that propels the spaceship forward. Plasma engines have far higher exhaust velocities than chemical rockets, making them suited for long-term space exploration. Plasma engines are distinct from ion thrust engines, which generate thrust by extracting an ion current from their plasma. In contrast to source ion thrusters, plasma engines utilize the currents and potentials created internally as a high current electric arc between two electrodes to accelerate the ions. This results in a lower exhaust velocity than ion thrusters while maintaining excellent efficiency and thrust. One of the primary advantages of plasma engines over other forms of propulsion is their efficiency. Plasma engines use less fuel than regular rockets, making them more cost-effective and environmentally benign. They also have a far longer life cycle, with some engines capable of functioning for years at a time. Furthermore, plasma engines can be throttled, controlling the spacecraft's speed and direction. Plasma engines also have the advantage of not requiring high-voltage grids, anodes, or cathodes to accelerate charged particles in the plasma source. This decreases the likelihood of grid ion erosion, while also simplifying engine design. Furthermore, the plasma exhaust is quasi-neutral, which means that positive ions and electrons coexist in equal proportions. This allows easy ion-electron recombination in the exhaust to extinguish the exhaust plume without using an electron gun. Typical examples of these new engines now create the source plasma utilizing a variety of ways, including radio frequency or microwave energy delivered via an external antenna. Plasma engines are versatile in fuel. Various propellants, including argon and carbon dioxide, can be used. Plasma engine development has advanced significantly, with prototypes being tested in various space missions, including NASA's Dawn mission to study the asteroid belt and the European Space Agency's Bepi Colombo mission to Mercury. However, plasma engines are still in their infancy, and much more study is required before they can be extensively employed for air transport. While plasma engines have immense potential for interstellar travel, they have several limitations. One important drawback is their tremendous energy consumption. The Vasimir VX200 engine, for example, takes a tremendous 200 kilowatts of electrical power to create only 1.12 pounds and 5 newtons of thrust, implying that such an engine would need a lot of energy to be suitable for space missions. A metaphor for understanding 5 Newton thrust is to think of pushing a light car on a flat road. With a force of about 5 Newton, you would be able to slowly set the car in motion and push it forward with a constant acceleration of 1 ms squared. The important thing to understand is that Newton is a unit of measurement for force, and 5 Newton of thrust represents a moderate but useful amount of force to set an object in motion or propel it forward. Furthermore, combining the engine with a fission reactor could increase the spacecraft's weight, making launching it into space more difficult. Plasma erosion, which can occur when the plasma thermally ablates the walls of the thruster chamber and support structure, is another important disadvantage. This might cause system failure, necessitating the development of new materials and cooling methods to prevent erosion. Plasma engines' limited thrust makes them unsuitable for putting a spaceship into orbit. Therefore, they're only useful for in-space operations. Chemical rockets have far more thrust and can be used to send spacecraft into orbit. Despite these disadvantages, numerous space agencies have created plasma propulsion systems such as NASA's Hall Effect Thruster, Busic's Vasimir engine, as well as the Vasimir engine produced by the Astro rocket firm. These engines have been tested in orbit and are promising to reduce travel time between planets. The creation of China's new plasma electric engine represents an important step forward in this industry. Before we continue, hit that like button and subscribe to our channel for interesting upcoming videos. This project is known as the CJ1000AX, and a team of engineers started working on it covertly in 2020. The Institute of Technological Sciences and Wuhan University demonstrated a functional prototype of a microwave thruster, claiming that it could operate in the Earth's atmosphere with comparable efficiency and thrust to conventional jet engines. This novel plasma engine operates on air and electricity rather than gases such as xenon, making it a more viable alternative for the Earth's atmosphere. The plasma engine generates thrust by rapidly heating and expanding plasma as a source gas. The novel engine generates low-temperature plasma from ionized air, which is then put into a tube and assaulted with microwaves. A microwave shapes the ions, enabling them to collide with non-ionized atoms and generate tremendous thrust further down the tube. The flattened waveguide and a 1 kilowatt 2.45 gigahertz magnetron specifically constructed focused the microwaves, increased the strength of the electric field, and hit the plasma with as much heat and pressure as possible. A quartz tube is also inserted into the waveguide's narrowest point. Air is pumped down this tube via a tiny waveguide section before exiting the core. The plasma rapidly heats over 1000 degrees Celsius at the other end, providing thrust as the hot gas exits the waveguide. Testing has revealed that the engine can generate up to 500 newtons of thrust in continuous operation for 30 minutes, which can be useful on current aircraft. To assess the amount of thrust produced by the engine, researchers discovered that finely tweaking the airflow in the compressor may produce a more stretched flame jet in response to higher microwave power. The team used a hollow steel ball filled with steel beads to balance it on top of the tube. They could counterbalance the gravitational forces acting on the thrust produced by the plasma jet by altering the ball's weight. The engine is extremely efficient, producing 2.45 pounds of thrust, or 11 newtons, for every 400 watts of electrical input and 1.45 cubic meters of air per hour, resulting in a conversion rate of 6.29 pounds of thrust, or 28 newtons, for every kilowatt of power consumed. Assuming a linear relationship between microwave power and thrust output, it may be conceivable to use a Tesla Model S battery with a capacity of 310 kilowatts to generate up to 1,911 pounds. 8.5 kilonewtons of propellant thrust force. This technology, however, has significant limitations. The engine's 1000-degree exhaust could represent major problems, and the airflows are around 1500 times lower than those of a full-sized engine, implying that thrust must scale by almost 4 orders of magnitude. Furthermore, the engine demands significant power, making it unsuitable for larger aircraft. Nonetheless, plasma engines, like the one developed lately by Chinese engineers, have the potential to transform air travel by providing a cleaner, more efficient means to power planes. Traditional jet engines rely on fossil fuel combustion, emitting hazardous pollutants into the atmosphere and contributing to climate change. Electricity is used to ionize the air, resulting in a plasma that produces a high-velocity stream of charged particles capable of generating thrust. One of the primary advantages of plasma engines is that they emit less carbon dioxide. According to a University of Illinois at Urbana-Champaign study, plasma engines could emit up to 60 less carbon than regular jet engines. That is a massive improvement on the current situation, and an insane big impact on sustainability and carbon footprint. Chinese experts tested the new plasma engine on a limited scale, and whether the technology can be scaled up to power commercial aircraft remains to be seen. This will necessitate major investment in research and resolving technical issues associated with electricity generation and storage. The engine may also overheat or malfunction, resulting in catastrophic failure. These safety concerns must be addressed before plasma engines may be adapted for commercial air travel. Although these are hints of progress in designing plasma engines for air travel, despite these hurdles. This game-changing innovation on the horizon prompts the question, what amazing enhancements may we achieve by fully utilizing plasma engines? What impact may this have on the future of transportation as we know it? Our expectation is that it's going to have a mega positive impact on CO2 emissions and make the aviation industry more sustainable. Leave your answers in the comments section below. And don't forget to like this video and subscribe to our channel if you haven't already.